Hello and welcome to this short little bonus video where I'm going to talk a little bit more in depth um, about open and closed sets in R2. So refresh your memory of what open and closed mean, right? Open means it consists entirely of interior points, and then a set is closed if it contains all of its boundary points. So I gave you examples in the last video of an open set and a closed set in R2. But there, like I mentioned in that video, there are sets that are both open and closed at the same time. So I'll give one example here. How about R2? How about the entire plane? Is it open? Is it closed? So we ask ourselves, okay, is it open? Does it consist entirely of interior points, or does it maybe contain some of its boundary points? Or does it contain all of its boundary points? So what is a boundary point for the plane? What is a boundary point for the plane? So are there any points in the plane such that every open disk around them contains a point outside of the set, that's R2, so outside of this set R2, and inside of the set R2? Well, no. There can't be any boundary points for this set, because if I'm in the plane and I draw an open disk around any point, necessarily everything around it is inside of the plane. So there are no points in the plane outside of R2, hence there are no boundary points. So answer, there are none. This set doesn't have any boundary points. And so what we say is vacuously, it contains all of its boundary points. It doesn't have any, and so it doesn't need to satisfy anything in order to contain its boundary points, right? It has them all because there aren't any. So I'll say vacuously, like a vacuum. Vacuously, R2 contains all of its boundary points. If that's a little weird for you, if you're still not believing me, I have another argument here. If you say that it doesn't contain its boundary points, then you need to be able to give me a boundary point that it doesn't contain. Can you do that? No, because there aren't any boundary points. That's the nature of something being vacuously true. There is no counterexample to it, and so it's sort of by default true. So there are no boundary points for this. So it contains all of its boundary points. That means it's closed. So R2 is closed. Is it open? Well, there's no boundary points, right? Every disk in R2, or every point in R2, every disk around that point is entirely enclosed in the region. And so all of R2 are interior points. So I'll say every point in R2 is an interior point. So it consists entirely of interior points, so it's also open. So the entire plane as a set is both closed and open, right? These definitions are not strictly opposites of each other. There are other examples of this. For instance, the null set or the empty set. So the set in R2 that doesn't contain any points, again, is closed and open. You can think about that one, work through the logic there. And then there are regions like the one we're going to deal with in the domain of this function. This domain is neither open nor closed. So why? No, sorry. No, this one is. No, this one does consist entirely of interior points. So no, sorry. This one is an open set. But if I say, if I also put an extra condition on this, so let me jump over here for a second. If I did the set, let's say xy in R2, such that, let's say it's inside of the closed unit disk, and let's say let's say we get rid of the origin. So I also add the condition that xy is not equal to 0, 0. So this would look like, right, everything in the closed unit disk, so like this, except for the origin. I'd have a little open dot around the origin. So this one, it has a boundary point, right? The origin is a boundary point, as well as everything around the unit disk. That's also a boundary point. It contains those boundary points, but it does not contain the origin, which is a boundary point. And so it doesn't contain all of its boundary points, which means that it's not closed. And then, does it consist entirely of interior points? No, because it does contain some boundary points, right? Right, it includes those boundary points around the end. So it contains some of its boundary points, but not all, and therefore it doesn't consist entirely of interior points, and so it's also not open. So something like this is neither closed nor open. So that can happen as well. So we can be closed and not open, we can be open and not closed, we can be both closed and open, or it could be neither closed nor open. All four possibilities exist. Closed and open are not opposites of each other. That's the whole point of this little extra video here. So if you watch this, I applaud your curiosity. Stay curious, keep asking questions, and you get fun stuff like this. All right. See you next time.